Swayam Prabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on turbulence. We just started the discussion on turbulence, and where we have stopped just looking at this thing, the problem of the sphere. So just to quickly review what we are going to do about this discussion on turbulence. We first look at what turbulence, their behavior of the turbulent flow, then we will try to characterize it, and then finally some of these processes which are involved and the modeling aspect. And then we started off this particular example and of the sphere. Now this one can see, as we just said, that drag force is function of Reynolds number and all these things. So there is a nice similarity between your cricket ball. If you have looked at it, usually the players rub it in one side and keep on rubbing it. So that means what they try to do, they try to keep one side shiny, and the other side to be rough. So they maintain that roughness and all these things to make an difference in the fluid dynamics features. Here everything is turbulent. Now if you make one side smooth and keep it shiny, the flow pattern will be different compared to the rough side. So that actually generates that kind of swing, and also depending on the speed and all these things, there are other issues like how the bowler actually bowl at what speed, then the lift it generates when hitting the pitch, and then the reverse swing. All these are associated with that, and this is an schematic. Now more if you look at it, so one hand, if you have things are turbulent, that sometimes reduces the overall drag. So this is the picture that we looked at in the earlier also. This is R equals to 15,000. So you see the boundary layer which separates near this point. So this is a separation point. Okay, that's a situation where the laminar boundary layer separates, because this particular Reynolds number 15,000, that belongs somewhere here. Okay, so that's with the increasing Reynolds number and the features of. So if you have separation point here, so there is a zone which will create the adverse pressure gradient, and you will get more drag force. So you experience more drag force. At the same time, same sphere, you go to a Reynolds number of 30,000, which is sort of a higher Reynolds number situation, which is a turbulent situation. So the tripping of the boundary layer or the separation point of the boundary layer has moved from this position to this position. So the zone which is having adverse pressure gradient zone, that is also, so from here to here, that is quite reduced. So what happens here physically, this turbulent boundary layer with the increasing Reynolds number, the turbulent boundary layer shifts this separator point towards the rear portion of the sphere or towards the rear stagnation point. So you have a smaller wake, and the smaller wake will reduce the overall drag. So this case you get reduced drag, and this case, so that means if you have a laminar boundary layer which separates, actually it creates more drag compared to a situation where if you have, and this is why when I talked about that cricket ball dynamics, see that is why the player actually rub the ball one side and keep it smooth on the other side. So, they try to make one side to be turbulent, where actually the separation point shifts towards the rear point, and other side it remain laminar where it separates earlier. So, if you see a situation of which one case it separates from here and other case it separates from here. So, obviously there would be an axisymmetric force. So, these two forces will be acting in a non-equal fashion and which will create that swing, but this is one aspect of it when the ball is actually traveling in air, but there are other issues like to generate that, I mean to reach to that Reynolds number or the speed. Now, the ball has to be thrown with that speed, then it has to hit the pitch, and then also that generates some sort of an lift force due to rotation and other thing. But if you leave those factors for the time being, and when you just think about one side smooth and one side rough, the ball is approaching towards the batsman, then that is where the swing happens because of this asymmetric in the radial forces. And the primarily the reason behind that is the fluid mechanics. One case it is a laminar separation, other case it is turbulent separation. So, this case the drag is reduced or the adverse pressure gradient zone is low, this case it is high. Now, going to some more different example of turbulent flow, these are again what you see in nature very often. So, this is an volcano actually in 2006 which erupted in Alaska, and you see this kind of smoke and all these things. This is nothing but the system is turbulent. Then another ash plume reacting height 19 kilometer 3 days before the climatic eruption of 15 June 1991. You see this huge structure. These are, now you think about the scale of these things. So, this is one hand you are looking at the macroscopic structure of it, and this is, I mean apparently it looks quite random in nature, chaotic in nature, and that in one single sentence one can characterize this particular flow physics, the turbulent qualitatively, is that purely random in nature or chaotic in nature. That is what one can define a flow to be turbulent. That is obviously in qualitative sense. When you go quantitatively, one has to properly characterize it based on scale, their length scale, time scale and other features. Some more which you see the smoke coming out of the cigarette, this is also the nice example of characteristics. Another realistic example, when there is an aircraft which is flying, you see the nice structure like this. So, which is basically vortices and generated by this airplane, that is a big structure. So, these are highly turbulent in nature. So, that is what one can look at it, different example of turbulence and the other application. Now, one of the important characteristics is scale similarity, who is what it says that there is a similarity of large scale structure for different Reynolds number. So, the left hand side picture which is at Ra 10 to the power 7, this is an wake of grounded tank ship leaking crude oil. So, the ship is leaking the crude oil and you see the kind of a structure here behind that, which is obviously turbulence in nature, there is no doubt about it. And the other side, this particular one, this is a flat plate, this is a flat plate and which is inclined at an angle, and you see the structure of the large scale structure. So, if you look at qualitatively these two structure, the large scale structure, they show some sort of a similarity, and this is what is meant here. This turbulent flow features, one of the characteristic of this turbulent flow features at different Reynolds number provided there in all turbulent regime, there is a similarity in large scale structure. This is what we call scale similarity. Okay. So, that means you take a flow behind a grounded tank, or you take a flow around a flat plate, or you take a flow around a sphere, the large scale structure would be similar in nature. That is the important point here. Now, this is a well known again characteristics so of turbulent flow. So, this is a flow through a perforated plate with some square perforation and smoke visualization. So, these are the source of these images, one can, if you are curious, you can look at it. So, the flow comes from this side and it goes out from this side. When it enters over the plate, this is a nice streamline one can see. I mean, rather these are nicely ordered lines, but then it goes through transition to turbulent. So, there is a transition zone and then finally it becomes completely turbulent. So, the flow initially is laminar, it become transition. So, that means in transition it will behave with the both the characteristics, with the laminar characteristics and transition characteristics, and then it become finally turbulent. So, you can see the effect of this flow when it becomes turbulent and goes through this different situation. Now, if you increase the range of scale, that will with the increasing Reynolds number. So, this is at Reynolds number 1500 and this is at 20,000. So, the large scale structure remain same. So, there is a scale similarity which talks about the large scale structure remains same, but with increasing the Reynolds number, the range of scale would also go up. That means, from this to this scale range has gone up. So, which essentially says you may have similarity of the large scale structure, but that does not guarantee that in the small scale structure would be of the same order. So, there could be huge increment in the other range of scale or the small scale structures, because so this is what this picture very nicely demonstrate, that what happens to this particular thing. Now, if you go to time series and time averaging of the turbulent jet kind of flame, this is the picture we have taken already mentioned about the source. So, this is the coordinate system x2 and x1. At any particular point, this is an instantaneous instantaneous velocity signal, and you can see how it is actually behaving. There is a huge chaotic, and this is at the same location when you get the time average velocity. So, the time averaged one will give you some sort of an mean profile at this particular location, and from the center line it will tell you either side of the z axis how it spreads. So, already we have seen for laminar jet there are two important things one needs to know to characterize this kind of jet flow is the jet spreading and jet spreading angle, which is related with the jet half width. So, whatever we have looked so far, if we summarize that, essentially as a properties of turbulence. In that sense, if we summarize, one point which one has to note is that it is unsteady and 3D. So, under which you can say it is irregular or chaotic in nature. It is characterized by vertical structure or eddies. You have multiple length scale. One end you have large scale, which essentially calls it macro structure, and that depends on geometry, depends on flow geometry, and small scale, which one can say microstructure. So, it depends on energy dissipation and other things. This is universal structure or something. Second, it is an high Reynolds number flow, which is large scale structure is independent of RE, which is called scale similarity. Third, this is dissipative in nature. That means rapid loss of energy. And fourth is it is quite effective in mixing, that is mass, momentum, heat, etc. So, this is one of the very interesting point why it is effective. I mean, when we say effective is mixing, and that is why in our reacting system or practical reacting system, one way to look at it, we want turbulence to be present there. Though turbulence itself is going to create a lot of other problem, or it creates, I mean, incurs a lot of challenges to handle it, but on the one hand we do want the turbulence to be present, which will make it more effective from the mixing point of view. Better mixing, we can always expect better reaction, complete reactions, which is another desired feature of a reacting system. So, these are the essentially one can think about the broader characteristics that or the properties of turbulence. So, in a simple word, one can think about it is a truly unsteady and three dimensional flow field which is chaotic in nature. Now, rest essentially are the secondary level characteristics, that large scale structure, small scale structure, dissipative, high Reynolds scale similarity and all these. But now we can do some talk about some coordinate system and convention. So, we have in the one hand we have this x, y which is v, z which is w. This is typically we do in a lab scale, and typically atmospheric combustion, atmosphere, the convention is this is x, this is y and this is z. Now, there is an Einstein summation convention. So, which will essentially make it in terms of initial notation, one can write U2 by x2 x3. Now, we will write material or substantial derivative, which is ddt of the del t plus uj del xj. So, these are the two things which will be commonly used while we will be discussing more about these things. Now, we will write our Navier-Stokes equation for incompressible flow. So, which is rho constant and viscosity constant. So, that is what we have mass conservation equation. So, that one can write in terms of del u by del xi equals to 0. Now, we have momentum conservation equation, which are essentially three equations, but we can write in one single equation del I by del t uj del xj equals to minus 1 by rho del p by del xi nu So, that is my momentum conservation. Here small p is nothing but the p minus rho gi xi. This is an so called modified pressure. So, this is the pressure minus hydrostatic contribution, and nu is the kinematic viscosity, which is nothing but mu by rho. Now, when you look at this mass and momentum conservation equation, we have total 4 equation and we got unknown 4, which is 3 velocity components and pressure. Okay. So, this is one can think about, you have number of equations to number of unknowns. So, this is an sort of closed systems of equations for given initial condition and boundary condition. Now, we look at is in what is well posed problem. What is that? Now, one can think about a closed system of partial differential equation. Closed system of PDEs can be defined as well posed for a given initial and for a given initial condition and boundary condition, and it can be said well posed if a solution exists, the solution is unique, which means only one solution exists. Third, the solution is stable for small perturbations in the initial condition and boundary condition. So, a closed system of PDEs can be said well posed for a given IC and BC if the solution is unique, that is only one solution exists and the solution is stable for small perturbation in the initial condition and boundary condition. So, that is how one define the well posed problem. Now, how the Navier-Stokes equation would look like? So, that we can see how Navier-Stokes equation, whether it is a well posed or an ill posed, because Navier-Stokes equation, if you talk about the incompressible constant density system, and which is a simple one, then you have mass, momentum and energy conservation, but if you consider only mass and momentum, and we can see whether that is ill posed or well posed. So, we will stop here and continue the discussion in the next lecture.